resolution discrepancy. I'm not sure whether this paper is going to be relevant outside outside object recognition, because of, let's see, I have a premonition that this is not going to be very useful. Let's see. So starting off, data augmentation is key to the training of neural networks for image classification. This paper shows that existing augmentations induce a significant discrepancy between the size of the objects seen by the classifier at train and test time. In fact, a lower train resolution improves the classification at test time. We then proposed a simple strategy to optimize the classifier performance that employs different train and test resolution. It relies on a computationally cheap fine-tuning of the network at the test resolution. This enables training strong classifiers using small training images, and therefore significantly reduce the training time. For instance, we obtained 77.1% top 1 accuracy on ImageNet with a Resonant 50 trained on 120 by 120 images, and 79.8% with one trained at 224 by 224. A Resnext 101 32 by 48 dimension pre-trained with weak supervision on 940 million 224 by 224 images, and further optimized with our technique for test resolution. I'm not familiar with the parameterization for Resnext. Maybe it will be achieves 86.4% top 1 accuracy and top 5 98%. To the best of our knowledge, this is the highest image single crop accuracy to date. Okay. So right away, this says that this is just because of data augmentation. Although I thought data augmentation was also applied during testing. Well, if you're gonna deploy the network, it's not gonna see augmentation. Okay. Well, but that's the point. I mean, sure. I guess it's talking about the actual the discrepancy between the probability distribution, like the probability of certain things appearing or not, or certain. Okay. Convolutional neural networks are used extensively in computer vision tasks such as image classification, object detection, in-painting, style transfer, and even image compression. In order to obtain the best possible performance from these models, the training and testing data distributions should match. However, often, data pre-processing procedures are different for training and testing. For instance, in image recognition, the current best training practice is to extract a rectangle with random coordinates from the image, which artificially increases the amount of training data. This region, which we call region of classification ROC, is then resized to obtain a crop of a fixed size in pixel that is fit to the CNN. At test time, the ROC is instead set to a square covering the central part of the image. At test time, the ROC is instead set to a square covering the central part of the image, which results in the exact extraction of a so-called center crop. This reflects the bias of photographers who tend to center important visual content. Thus, while the crop extracted at training and test time have the same size, they arise from different ROCs, which skews the distribution of data seen by the CNN. Over the years, training and testing pre-processing procedures have evolved to involve the performance of CNNs. Over the years, training and testing pre-processing procedures have evolved to improve the performance of CNNs, but so far they have been optimized separately. In this paper, we first show that separate optimization has led to a significant distribution shift between training and testing regimes. Oh, there's an update. Since the publication of this paper at NeurIPS, we have improved the state of the art by applying our method to EfficientNet. See our note 39 for results and details. 39. Fix efficient and 2020. Okay. Wait, let me check. Fix efficient net. Fix efficient net. How many pages is this? Oh, they're cited by 15 already. This note complements the paper. Okay. First, we show the strategy is advantageous combined with recent training recipes from the literature. Most importantly, we provide new results for the efficient net architecture. The resulting network called. Okay. With a detrimental effect on the test time performance of models. We then show that this problem can be solved by jointly optimizing the choice of the resolution and scale at training and test time, while keeping the same ROC sampling. Our strategy only requires to fine-tune 2 layers in order to compensate for the shift in statistics caused by the change of the crop size. This allows us to retain the advantages of existing pre-processing protocols for training and testing, including augmenting the training data. Again, this allows us to retrain the advantages of existing pre-processing protocol. Allows us to retain the advantages of existing pre-processing protocols for training and testing, including augmenting the training data while compensating for the distribution shift. Our approach is based on a rigorous analysis of the effect of pre-processing on the statistics of natural images, which shows that increasing the size of the crops used at test time compensates for randomly sampling the ROCs at training time. Again, which shows that increasing the size of the crops used at test time compensates for randomly sampling the ROCs at training time. This analysis also shows that we need to use lower resolution crops at training than at test time. This significantly impacts the processing time. Halving the crop resolution leads to a threefold reduction in the network evaluation speed and reduces significantly the memory consumption for a typical CNN, which is especially important for training on GPUs. For instance, for a target test of resolution of 224, training at resolution 160 provides better results than the standard practice of training at resolution 224 by 224, while being more efficient. In addition, we can adapt a Resonant 50 train at resolution 224 by 224 for the test resolution 320 by 320 and thus obtain top 1 accuracy 79.8% single crop on ImageNet. Alternatively, we leverage the improved efficiency to train high accuracy models that operate at much higher resolution at test time while still training quickly. For instance, we achieve top 1 accuracy of 86.4% single crop on ImageNet with the Resonant 101 32 by 48D pre-trained in weekly supervised fashion on 940 million public images. Finally, our method makes it possible to save GPU memory, which could in turn be exploited by optimization. Employing larger batch sizes usually leads to a better final performance. Okay. Related work. Image classification is a core problem in computer vision. It is used as a benchmark task by the community to measure progress. Models pre-trained for image classification, usually on ImageNet database, transfer to a variety of other applications. Furthermore, advances in image classification translates to improved results on many other tasks. Recent research in image classification has demonstrated improved performance by considering larger networks and higher resolution images. For instance, the state-of-the-art in ImageNet benchmark is currently held by Resonant 101 32 by 48D architecture with 829 million parameters using 224 by 224 images for training. The state-of-the-art for a model learned from scratch is currently held by the EfficientNet B7 with 66 million parameters using 600 by 600 images for training. In this paper, we focus on Resonant 50 architecture due to its good accuracy to cost trade-off, 25.6 million parameters, and its popularity. We also conduct some experiment. Wait. We also conduct some experiments using the PNAS Net 5 large. This is the neural architecture search. Yeah. Architecture that exhibits good performance in ImageNet with a reasonable training and training time and number of parameters, 86.1 million, with the Resonant weekly supervised because it was the network publicly available with the best performance on ImageNet. Data augmentation. Data augmentation is routinely employed at training time to improve model generalization and reduce overfitting. Typical transformations include random size crop, horizontal flip, color jitter. In our paper, we adopt the standard set of augmentations usually commonly used in image classification. As a reference, we consider the default models in PyTorch library. The accuracy is also improved by combining multiple data augmentations at test time. The accuracy is also improved by combining multiple data augmentations at test time. Although this means that several forward passes are required to classify one image. Wait, what? Combining multiple data augmentations at test time. Although this means that several forward passes are required. Several forward passes. Why? To classify one image. For example, 13, 20, and 35 use 10 crops, one central, one for each corner of the image, and their mirrored versions. Another performance boost. Okay. Yeah, okay. Different version of the same image. So for test, I see. Accuracy is also improved by combining multiple data augmentations at this time. So instead of passing the image one time, you actually do multiple augmentations and get multiple results. But how do you? I'm guessing it's like the most votes you get. Another performance boosting strategy is to classify an image by feeding it at multiple resolutions. Again, averaging the predictions. Averaging the predictions. They didn't mention averaged. Okay. More recently, multi-scale strategies such as the feature permanent network have been proposed to directly integrate multiple resolutions into the network, both at train and test time, with significant gains in category level detection. Okay. Feature pooling. A recent approach employs p-pooling instead of average pooling to adapt the network to test resolutions significantly higher than the training resolution. The authors show that this improves the network's performance in accordance with the conclusions drawn by Fourier. Similar pooling techniques have been employed in image retrieval for a few years, where high resolution images are required to achieve competitive performance. These pooling strategies are combined or replace the RMAC pooling method. Or combine, which aggregates set of regions extracted at lower resolution. Okay, is this page out of order? No. Region selection and scale statistics. Applying convolutional neural network classifier to an image generally requires to pre-process the image. One of the key steps involves selecting a rectangular region in the input image, which we call region of classification. The ROC is then extracted and resized to a square crop of a size compatible with the CNN. AlexNet requires 224 by 224. While this process is simple, in practice it has two subtle but significant effects on how the image data is presented to the CNN. First, the resizing operator changes the apparent size of the objects in the image. Section 3.1. This is important because differently from translation, CNNs do not have a predictable response to a scale change. Pretty much. Yeah. Second, the choice of different crop sizes for architectures such as resonance that admit non-fixed inputs. Wait. The choice of different crop sizes that admit non-fixed inputs has the effect on the statistics of the network activations, especially after the global pooling global pooling layers. So since Resonant is fully convolutional with global pooling last two layers, you don't so it doesn't matter the size of the initial image that you pass in, that the filter can basically scan the image. But no, it does have, because after there is pooling, the pooling steps in between. Oh no, Resident doesn't have pooling, right? Yeah, I think Resonant stays 50 layers same. So 50 layers just doing convolution. That's why it's massive in memory size. Yeah. So if we can use a big, so the same, and at the end there is a global, global pooling that makes, makes them into this. It's like gathering evidence. So like the number of the filters is basically, so these are the pixels, the width and height, and this is the depth. So this is the depth, and width and height only rely on the width and height of the original image, and the convolution filter basically just sweeps this without a problem. So you start with an image, colored image with depth of 3, and sweeps and produces the same width and height but different depth. At the end, you can global pooling. You can, each slice of these gets pulled into 1 pixel, and basically at the end you have, if it's ImageNet, it's 1,000 categories, right? So at the end there would be 1,000 categories. Like C would be 1,000, and each one, basically each slice, is essentially something like was this object of, like, was this class detected anywhere in the image? Since you're pulling the entire image into 1 pixel, at the end is saying, is there evidence or is there heat that this object of category C was detected in this or not? So okay. Second, the choice of different crop sizes for architectures such as Resonant that admit non-fixed inputs has an effect on the statistics of the network activations, especially after global pooling layers. This section, so basically, imagine 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 a small deer, right? A small deer in a big image. Okay, and imagine the network can find the deer information, and you wanna classify whether this is a deer or not. It's supposed to be a deer, but if the deer is, for example, taking the bulk of the image, then imagine that the heat map in one of the seas, which looks for deer, for example, has all this part lighting up, saying, yeah, there's deer here. These are pixels of deer. Okay, then if you're doing global average pooling, then basically you're averaging the heat map over this for this category, and you say, yeah, I'm seeing like 40% or 0.4 deer here. Okay. Whereas if the deer is, imagine the deer is very small. Okay, so the pixels basically very localized here. Now you're saying 0.2% deer here, right? So that's no bueno, because now the balance is out of whack. For global pooling layers, this is a problem. This is problematic, right? Because now global pooling basically pools over the entire. So you're either saying the heat map has to overcompensate and give me higher, bigger heat map, or be much higher in value, whatever that location is, much higher in value. So yeah, the statistics of the output is increased. So let's say the actual value of the pixel in the 1,000, so that it can compensate when values of all the pixels are averaged. You can say, yeah, there is a signal here. There's strong signal here. So yeah, so that's statistics. But when the object is spread out, it has to give you it could still give you a bigger sim. Well, it has to. At certain point, because it doesn't know prior. Yeah, because it doesn't know exactly the size of the image that it's gonna see in the test. So it's gonna depend on the strength of the signal that it had learned to produce, so that it's effective for the training time. But it doesn't mean that if the image in the testing, imagine if you train on big objects, right? But on the test you have smaller object. No, actually it's the other way around. If you have in the training, no, it's correct. It's correct. So train on big, the signal is not strong enough, but since number of pixels at the heat cam and the global averaging is big, you can still have a strong signal. Like 60% of the pixels belong to the deer, and none of them is particularly very powerful. Let's say the values in the tens, right? While zeros are here. So it's like, yeah. But if your test is now small deer, it hasn't learned, the network hasn't learned to output a big signal for this deer because it's small, right? So you still end up with pixels that are in the tens, even for the small deer, which will make the statistics out of whack, right? It should be higher to, because the image is the same size. Sorry, the image is the same size. The deer is small. Now, because the statistics are out of whack, this deer is not 60% of the image, but rather 0.2%. So it has to supposedly, in order for this signal to be as significant as this one, this has to be like 3 times more radiant, right, or more illuminating here, so that after the averaging, it has the same strength when it's time to do the softmax, right? So that's that's how it affects. Okay. This section analyzes in detail these two effects. In the discussion, we use the following conventions. The input image is the original training or testing image. The ROC is a rectangle in the input image, and the crop is okay. Again, I'm not concentrating. This section analyzes in detail the two effects. In this discussion, we use the following conventions. The input image is the original image or testing image. Original training or testing image. The ROC is a rectangle in the input image, and the crop is the pixels of the ROC rescaled with bilinear interpolation to a fixed resolution, then fed to the CNN. Okay. Scale and apparent object size. If a CNN is to acquire a scale invariant behavior for object recognition, it must learn it from data. However, resizing the input images in pre-processing changes the distribution of object sizes. Resizing the input images in pre-processing changes the distribution of object sizes, of course, since different pre-processing protocols are used at training and testing time. The size distribution differs in the two cases. This is quantified next. There's a footnote. The reason for this difference is the following. At training time, extraction and resizing of the ROC is used as an opportunity to augment the data by randomly altering the scale of the objects. In this manner, the CNN is stimulated to be invariant to a wider range of object scales. Yeah, but at test times, it's not the same distribution, so yeah. So it makes the testing distributions lopsided to centered images. Or more biased towards centered images. Relation between the apparent and actual object sizes. We consider the following imaging model. The camera projects the 3D world onto a 2D image, so the apparent size of the objects is inversely proportional to their distance from the camera. For simplicity, we model a 3D object as an upright square of height and width r by r. Its depth is irrelevant. The r and r. Okay. The 3D object sits at distance z from the camera and is front to parallel to it. Okay. Hence, the image is r and r rectangle, where the apparent size r is given by r over z times f, where f is the focal length of the camera. Thus, we can express the apparent size as a product r equals f r1 of the focal length f, which depends on the camera, and variable r1 equals r over z, whose distribution pr is camera independent. Okay. Yeah, camera independent because it just depends on the size of the actual object and the distance from the camera. F is the camera dependent object, like lens dependent. While the focal length is variable, the field of view angle of most cameras is usually in the 40 to 60 degrees range. Hence, for an image of size H and width W, one can write F equals K square root of HW, where K inverse is 2 tan, which is equal to 1, is approximately constant. With this definition for F, the apparent size R is expressed in pixels. Okay, all of this is camera jargon I really don't care about. Effect of image preprocessing on the apparent object size. Now we consider the effect of rescaling the image on the apparent size of objects. If an object has an extent of r by r pixels in the input image, and if S is the scaling factor between input image and the crop, then by the time the object is analyzed by the CNN, it will have the new size rs times rs pixels. The scaling factor is determined by the preprocessing protocol discussed next. Train time scale augmentation. As a prototype augmentation protocol, we consider random resize crop in PyTorch, which is very similar to augmentations used by other toolkits such as Caffe and the original AlexNet. Random resize crop takes an input as an input an H by W image, selects ROC at random, resizes the latter to output a K train by K train crop. The ROC extent is is obtained by first sampling a scale parameter such that sigma square is between a sigma squared negative and a sigma squared positive, and an aspect ratio alpha that ln alpha is between ln alpha negative and ln alpha positive. Then the size of the ROC in the input image is set to HROC. WROC is equal to square root sigma alpha HW sigma alpha. Wait, what? Oh, okay. Sigma alpha HW sigma alpha W over H. The ROC is resized anisotropically with factors K train over H rock, K train over R to generate the output image, assuming for simplicity that the input image is square and that alpha is 1. Scaling factor for input image to output crop is given by By scaling the image in this manner, so this is the scaling. By scaling the image in this manner, the apparent size of the object becomes R train becomes S times R. So SF times R. So K train over sigma R1. Since K train is constant different from R train does not depend on the size HW of the input image. Hence, preprocessing standardizes the apparent sizes, which otherwise would depend on the image resolution, input image resolution. This is important as networks do not have built-in scale invariance. What are you trying to say? Actually, all you're saying is that the size of the object is independent of the rescaling of the size of the object is independent of the well, why would the rescaling depend on the resolution? Test time scale augmentation. As noted above, test time augmentation usually differs from train time augmentation. The former usually amounts to isotropically resizing. The former usually amounts to isotropically resizing the image so that the shorter dimension k and the shorter dimension is k test image, and then extract a k test by k test crop center crop from that under the scaling factor from the input image to crop rewrite as k. This has a similar standardization effect as the train time augmentation. Lack of calibration. Compare equation 2 and 3. We conclude that the same input image containing an object of size R1 results in two different apparent sizes if the training or testing preprocessing is used. Well, duh. These two sizes are related by, well, the size, R test and R train. In practice, for standard networks such as AlexNet, K test image and K train however, the scaling factor sigma is sampled with square law seen above in the range. Hence, at testing time, the Hence, at testing time, the same object may appear as small as a third of what it appears at training time. For standard values of the pre-processing parameters, the expected values of this ratio with respect to sigma is okay. Where f captures all the sampling parameters. Okay. Scale and activation statistics. Okay, so you don't have to go over. I might not be very. Since it's a different operation, this is random resize crop versus center crop, which doesn't do resize. All I understood from this is that now everything with a different ratio of resizing, k-train and k-test image and k-train, sorry, the final resolution of the image, since that's the all, like, I could have conjured this just by telling me you do I have an object here and an object in the test, an object in the training. This is sized k train, and this is sized k test, and I'm resizing this with sigma that is drawn from point. Well, it's the square. Yeah. .28 square to 1 square root underscore sampled from this. Yeah. All I would have told you, yeah, directly that the ratio this to this would have been this. Like, doesn't need. I don't know. In addition to affecting the apparent size of the object, pre-processing also affects the activation statistics of the CNN, especially if its architecture allows changing the size of the input crop. We first look at the receptive field size of CNN in the previous layer. This is the number of input spatial locations that affect the response. For the convolutional part of the CNN, comprising linear convolution, subsampling, ReLU, and similar layers, changing the input crop size is approximately transparent because the receptive field is unaffected by the input size. However, for classification, the network must be terminated by a pooling operator, usually average pooling, in order to produce the effect size vector. Changing the size of the input crop strongly affects the activation statistics of this layer. Yeah, we alluded to that before. Activation statistics. We measure distribution of activation statistics, activation values after average pooling in Resonant. As it is applied on a ReLU output, all values are non-negative. At this default crop resolution of ktest ktrain T20, the activation map is 7 by 7 with a depth of 2048. At ktest 64, the activation map is only 2 by 2, pulling only zero values. Pulling only zero values becomes more likely. Pulling only zero values becomes more likely, and activations are more sparse at the rate of zeros. As activations are more sparse, the rate of zeros increases from 0.5% to 29.8%. The values are also more spread out. The fraction of values above 2 increases from 1.2 to 11.9. Increasing the resolution reverts the effect. With ktest 400-420, the activation map is 14 by 14. The output is less sparse and less spread out. I already said that this simple statistical observation shows that if distribution of activation changes at test time, the values are not in the range that the final classifier layer were trained for. Yeah, I mentioned that. Okay, that's an easy. Like it's an intuitive thing to Okay, and I'm back. Sorry about this. Uh, is anybody watching? Probably not. Yeah. Okay. Never mind. Okay, just going back. Despite the fact that larger test crops result in better accuracy. Despite the fact that increasing the crop size affects the activation statistics, it is generally beneficial for accuracy, since, as discussed before, it reduces the train test object size mismatch. For instance, the accuracy of Resonant on ImageNet validation set as k-test is changed. Okay, k-test. Okay. Thus, for k-test equals 228, the accuracy is 78%, which is greater than 77 obtained for the native crop size equals 224 in training. In figure 5, we see this result is general. Better accuracy is obtained with higher resolution crop at test times than at train time. In the next section, we explain and leverage this discrepancy by adjusting the network's weights. Method. Based on the analysis of section 3, we propose two improvements to the standard setting. First, we show that the difference in apparent object sizes at training and testing time can be removed by increasing the crop size at test time, which explains the empirical observation of section 3.3. Second, we slightly adjust the network before the global average pooling layer in order to compensate for the change in activation statistics due to the increased size of the input crop. Calibrating the object size by adjusting the crop size. Equation 5 estimates the change in the apparent object sizes during training and testing. If the size of the intermediate image K image test is increased by a factor of alpha, where alpha is 1 over 0.8 equals 125 in the example, then at test time the apparent size of the object is increased by the same factor. This equalizes the effect of the training preprocessing that tends to zoom on the object. However, increasing k-test image with k-test fixed means looking at a smaller part of the object. This is not ideal. The object you identify is often well framed by the photographer, so the crop may show only a detail of the object or miss it altogether. Hence, in addition to increasing k-test image, we also increase the crop size k-test to keep the ratio k-test to k-image constant. However, this means that k-test greater than k-train, which skews the activation statistics section 3.2. The next section shows how to compensate for this skew, adjusting the statistics before spatial pooling. At this point, we have selected the correct test resolution for the crop, but we have skewed activation statistics. Hereafter, we explore two approaches to compensate for this skew. Parametric adaptation. We fit the output of the average pooling layer with a parametric Fréchet distribution at the original k-train and the final k-test resolutions. We fit the output of with a parametric fit. Then we define an equalization mapping from the new distribution back to the old one via scalar transformation, and apply it as an activation function after the pooling layer. See Appendix A. This compensation provides a measurable but limited improvement on accuracy, probably because the model is too simple and does not differentiate the distribution of different components going through the pooling operator. Adaptation via fine-tuning. Increasing the crop resolution at test time is effectively a domain shift. A natural way to compensate for this shift is to fine-tune the model. In our case, we fine-tune on the same training set after switching from k-train to k-test. Here, we choose to restrict the fine-tuning to the very last layers of the network. A takeaway from the distribution analysis is that the sparsity should be adapted. This requires at least to include the batch normalization that precedes the global pooling into the fine-tuning. In this way, the batch statistics are adapted to the increased resolution. We also use the test augmentation. We also use the test time augmentation scheme during fine-tuning to avoid incurring further domain shifts. Figure 4 shows the pooling operator's activation statistics before and after fine-tuning. After fine-tuning, the activation statistics closely resemble the train time statistics. This hints that the adaptation is successful. However, as discussed above, this does not imply an improvement in accuracy. CDF of the activations on the output of the average pooling layer for a Resonant 50 when tested at different resolutions k-test. different resolutions. K-test. Compare the state before and after fine-tuning the batch norm. Okay. So I'm guessing what they do here is still using the same training set, but applying the testing pre-processing and observing the change in the statistics. And fine-tune means they backpropagate to make it work well. Okay, but they only do that for the final. Yeah. Restrict the fine-tuning, the very last layers of the network. To avoid incurring further domain shifts. We also use the test time augmentation scheme during the fine-tuning. Okay. So after fine-tuning, it's more in line with the reference. Experiments. Benchmark data. We experimented on the ImageNet 2012 benchmark, reporting validation performance as top 1 accuracy. It has been argued that this measure is sensitive to errors in ImageNet labels. However, the top 5 metric, which is more robust, tends to saturate with more modern architectures, while top 1 accuracy is more sensitive to improvements in the model. To assess the significance of our results, we compute the standard deviation of the top 1 accuracy. We classify validation images, split into a set of 10 folds, and measure the accuracy on 9 of them, leaving 1 out in turn. The standard deviation accuracy over 10 folds is 0.03% for all settings. Thus, we report 1 significant digit in accuracy percentage. Yeah. In the supplemental material, we also report results on the fine-grained visual categorization challenges, iNaturalist, and Herbanium. Herbarium. Okay. Architectures. We use standard state-of-the-art natural neural networks with no modifications. We consider, in particular, Resonant 50. For larger experiments, we use PNAS Net 5 large, learned using neural architecture search as a succession of the interconnected cells. It is accurate 82 0.9 top 1%, top 1 accuracy, with relatively few parameters, 86 million. Okay, we also use Resnext 101, 32, 42, whatever, pre-trained weekly, supervised 940 million public images with 1.5k hashtags matching with 1000 ImageNet 1k sets. Its accuracy rate is 85.4, top 1 with a lot of parameters. Yeah, closing to a billion. Training protocol. We train Resonant 50 with SGD, learning rate of 0.1. That's high. Batch size, 0.1 times B over 256, where B is the batch size, as in 15. What is 15? So wise in the ways of science. Bag of tricks for image classification with convolution neural networks. Okay. The learning rate is divided by 10 every 30 epochs, with a repeated augmentation of 3. An epoch processes 5,005 times 512 over B batches. Or 90% of the training images. 90% of the training images. C5. 5. What is 5? Multi-grain, a unified image embedding for classes and instances. Okay. In the initial training, we use B512, 120 epochs, and the default PyTorch data augmentation. Horizontal flip, random resize crop as in section 3, and color jittering. To fine-tune, the image learning rate is 0.008, same decay, B equals 512, 60 epochs. The data augmentation for fine-tuning is described in the next paragraph. For Resnext 101, 32 times 48D, we use pre-trained version from PyTorch Hub repository. We also we use almost the same fine-tuning as for the Resonant 50. Almost. We also use a 10 times smaller learning rate and batch size 2 times smaller. For PNAS net 5 large, we use the pre-trained version and Cadine's GitHub repository. The difference with Resonant 50 fine-tuning is that we modify the last 3 cells in one epoch and with a learning rate of 0.0008. We run our experiments on machines with 8 Tesla V100 GPUs and 80 CPU cores to train and fine-tune our Resonant 50. Fine-tuning data augmentation. We experimented 3 data augmentations for fine-tuning. First one, test DA, is resizing the image and then take the center crop. The second one, test DA2, resizing the image, random horizontal shift of the center crop, random horizontal flip, color jittering. The last one, train DA, is the train time data augmentation as described in the previous paragraph. Why would you fine tune with the train DA? The whole point is that train DA creates. I mean, the size of the crop is different, but yeah, okay. A comparison of the performance of these data augmentation is made in section C. The test DA data augmentation described in this paragraph being the simplest, therefore test DA is used for all results reported with Resonant 50 and PNAS 5 large. In this paper, except in table 2, where we used test DA2 to have slightly better performances in order to compare our results with the state of the art. For ResNet Next 10132D, all reported results are obtained with test DA2. We make a comparison of the result obtained between test DA2, and test DA in section C. The baseline experiments is to increase the resolution without adaptation. Baseline experiment is, Repeated augmentations already improve the default PyTorch Resonant 50 from 76.2 to point accuracy to 77.0. Figure 5 left. Okay. Figure 5 left shows the increasing the resolution at the test time increases the accuracy of all our networks. E.g., the accuracy of a ResNet trained at resolution 224 increases from 77.8 to 78.4 top 1 accuracy at an improvement of 1.4 percentage point. This concurs with prior findings in the literature. Figure 5 left. Top 1% accuracy of Resonant 50 turning to test time resolution. Left, without adaptation, just increasing the, right after train resolution. What? Oh, train resolution 64. So trained on 64, tested on 96. I see top 1 accuracy is being here, right? Here. Yeah. Trained on 384 and tested on 448. Okay. The numerical results are reported in Appendix C. Comparison of the results right after resolution adaptation. Result. Improvement of our approach on Resonant 50. Figure 5 right shows the results obtained after fine-tuning the last batch norm in addition to the classifier. With fine-tuning, we get the best result, 79%, with classic Resonant 50 trained at 224, compared when there is no fine-tuning. The k-test at which the maximum accuracy is obtained increases from 228 to 384. If we prefer to reduce the training resolution, k-train 128 and testing testing at k-test should be k-test, right? Testing at k-test equals 224 yields 77.1 accuracy, which is above the baseline trained at full test resolution without fine-tuning. Multiple resolutions. To improve the accuracy, we classify the images at several resolutions and average the classification scores. Thus, the training time remains the same, but is a modest increase in the inference time compared to processing only high-resolution crop. To improve accuracy, we classify the images at several resolutions and average the classification scores. Thus, the training time remains the same, but there is a modest increase in inference time compared to processing only the highest resolution crop. With k-train 128 and k-test both 256 and 192, the accuracy is 78%. K-train 224 and k-test 384, 352, we improve the single crop result from 79.0 to 79.5. Application to larger. At this point, I'm not sure what to take from this. Application to larger network. The same adaptation method can be applied to any convolutional network. Well, okay. In table 1, we report the result on PNAS 5 large and the IGM, whatever is next. For PNAS 5, we found it beneficial to fine-tune more than just the batch normalization and the classifier. Therefore, we experiment with fine-tuning the last the three last cells by increasing the resolution k-test to 480. The accuracy increases by 1 percentage point. By combining this with an ensemble of 10 crops at test time, we obtain 83.9 accuracy. With the Resnext increasing the resolution k-test 320, the accuracy increases by 1 percentage point, thus reached 86.4 top 1 accuracy. Speed accuracy trade-off. We consider the trade-off between training time and accuracy normalized as if it was run on one GPU. The full table with timings are in supplementary section C. In the initial training stage, the forward pass is 3 to 6 times faster than the backward pass. However, during fine-tuning, the ratio is inverted because the backward pass is applied only to the last layer. In the low-resolution training regime, k equals 128, the additional fine-tuning required by our method increases the training time from 111.8 hours to 124 hours, so an increase of 11%. This is to obtain accuracy of 77.1%, which outperforms the network trained at native resolution 22.4 in 133.9 hours. we produce a fine-tuned network with k-test equals to 384 that obtains higher accuracy than the network trained natively at that resolution. And the training is 2.3 times faster, 151.5 hours instead of 348.5 hours. Abelation study. We study the contribution of the different choices to the performance limited to k-train equals 128 and k-train equals 224 by simply fine-tuning the classifier, the fully connected layers of Resonant 50. With the test time augmentation, we reach 78.9% in top 1 accuracy with the classic Resonant 50 initially trained at resolution 224. The batch norm fine-tuning and improvement in data augmentation advances it to 79.8%, 0.0%. The higher the difference in resolution between the training and the testing, more important batch norm fine-tuning to adapt to the data augmentation. The full results are in the supplementary section C. Beyond the current state of the art, Table 2 compares our results with competitive methods in the literature. Our Resonant 50 is slightly worse than Resonant 50D and multigrain, but these do not have exactly the same architecture. On the other hand, our Resonant 50 cut mix, which has a classic Resonant 50 architecture, outperforms other Resonant 50, including the slightly modified version. What is cut mix? Conclusion. We have studied extensively the effect of using different train and test scale augmentations on the statistics of natural images and of the network's pooling activation. We have shown that by adjusting the crop resolution, a simple and lightweight parameter adaptation, it is possible to increase the accuracy of standard classifiers significantly by everything being equal otherwise. We have everything being equal otherwise. We have also shown that the researchers waste resources when both training and testing strong networks at resolution 224 by 224. We introduce a method that can fix these networks post facto and thus improve their performance. An open source implementation. Yeah, but this is only for image classification. You cannot do this for stuff that is not image classification. Natural image classification. That's what I'm trying to say. If the image has to have specific, like the objects cannot be in skew position or, yeah, I don't know what to take from this paper. I guess I'm not really, well, this is gonna stay, like, I'm gonna keep this in mind if I ever employ data augmentation. I'd come back to this paper and maybe read it between the detail, between the lines. Yeah, okay. I'm guessing few other papers might be more interesting for the time being. Consistency realization for GAN. Unit discriminator. This is for giving, like, saying which part is the discriminator. I'm guessing, yeah, saying is real or fake. Yeah, and this is what investigate loss functions. Well, no, not really. Yeah, LP 55, 555. These are metrics for LPIPS 55. 46, what is 46? So what is 5? 5 is what? The 2018 Prim Challenge on Perceptual Image Super Resolution. Okay. What is 46? Image quality assessment from error visibility to structural similarity. Okay. 55. Alexievros. Okay. The unreasonable ineffectiveness of deep features as perceptual metric. Okay, this sounds like a good paper. Okay, I will read this tomorrow. No, I have Okay. And stop recording now. Stop streaming. Yeah, thank you for